Welcome to another Ultralight Airplane Structural Analysis video from the Ultralight Airplane Workshop. I'm Leon. This video is part 5 of a multi-series video on doing analysis and testing on the nose rib for the UWS-4 ultralight airplane. And when I say ultralight airplane, I mean an ultralight airplane that matches the Part 103 regulations here in the United States. If you haven't watched the previous videos in the series, you might want to do that because you could possibly be a little bit lost when I'm talking about various things here. And at least look at part 4 where you'll see how I assembled this. Well, except for these tabs here. So first, here in this intro, I'm going to talk about what I've done since I ended part 4. I did a little bit of work in preparation for assembling the test stand. Now, number one, I needed a way of putting the stress over each of the rivets here on this rib. And the way I did that is I made some of these tabs. This is a little bit thicker aluminum. Now the skin here is 16 thousandths of an inch aluminum. I did some 20 thousandths and 25 thousandths here to make these tabs. And then I bent the tab right here where I made this little hole. I meant right here in the middle. And I bent them just enough so that when this hole is sitting directly over the middle of a rivet, that it'll be vertical. That way when I'm pulling up, I'm pulling pretty much straight. Now, one of the things I did here that may or may not work, I just do not know, is I used super glue to glue these tabs on here. Now, I did make a mistake. I realized last night when I was laying in bed, I realized I made a mistake when I was preparing the surfaces here. I cleaned the surface on the wing and on the bottom of the tabs with acetone, getting all the grease off of them. Then I Scotch-Brited them. But that's where I made a mistake, or right after that. I neglected to clean off the surface again because there's going to be a very fine aluminum dust on there, and I forgot to clean that off. So there is a little bit of aluminum dust on each side of the glue in here. So that's not good. That's going to weaken the joint. But I do think it's strong enough to hold because, let's see, I think I used this one. I think this is the one. Yeah, I can pick it up using it. So hopefully it'll work. I don't need more than, let's see, 13, 6.5, 9, almost 20 pounds of force. So it's possible some of these will break off. I don't know. So what I'll do as a backup plan is I'll put a rivet on each side of this hole, and that'll hold it without any problem at all. Another thing that I did is on my Whipple tree here. Now, I've shown it in past videos, and it was flopping around because when I'm in test mode, I need each of these bolts on here to move freely. But while I'm setting this up, I don't want it flopping around because it's heavier on the back than on the front, and so it's going to tilt. So I tightened all these down so they wouldn't move so that I'll be able to come down here and hook these wires into each of these holes to put the load on. Then, right before I start testing, I'll loosen these bolts up just enough so that they can move. Another thing that I did is, if I decide I want to use this link in here, there's a eye bolt screw, which you'll see shortly, in the top of the test stand that I put the link through, or at least I've been thinking of doing that, and then hooking this hydraulic ram on. And then the pressure, of course, will pull up, pulling up on the rib. But it didn't want to go in here freely, so I ended up doing a little bit of grinding here on the edge of this hook. But I might just put this hook straight on that eye bolt. I haven't decided yet. Now, just as a reminder, there's also going to be a load cell on here so I can measure the load. And then this will be attached to the bottom of the test stand. Load cell will be hooked on one end of the ram and then on the other end of the Whipple tree. And just as a reminder, or in case you haven't watched some of the previous parts, the load I want to put on this rib is the load that the center rib of the wing would see at maximum G. That's going to be 3.8 Gs with an additional 50% of safety factor. Now it turns out that 3.8 Gs on that center rib here on the nose is 86 pounds if I remember correctly. If I'm not remembering correctly, I'll put a pop-up here that shows you exactly what it is from the spreadsheet. And then I'd multiply that by 1.5, and that gives the total load that I want to put on this thing. Now, at 86 pounds, I want this to be able, even though it might deflect, once that load is released, I want it to go all the way back to where it started. But if I have a load greater than 86 pounds, I'm allowed to have some permanent deflection. But I don't want to have a complete failure until we at least get to that 1.5 safety factor. So that's the plan. So we'll put a load on this. We'll start gradually increasing it. We'll see if any of these tabs start popping off a little prematurely. We'll see if some of my test stand fails. Could be. We'll see if any of the Whipple tree fails. That's always a possibility. I doubt that it will. And we'll start increasing the load, watching the load on the load cell until we get up to 86 pounds. And then I'm going to release the load and see if I can see any permanent damage on the rib. Now, if the answer is yes, I got a problem. I got to redesign the rib. If the answer is no, then we're going to go ahead and start putting that load in until we get all the way up to the safety factor. And then we'll release the pressure and see what we got. I imagine there'll be some permanent damage, but that's okay as long as it hasn't completely failed. Let's get going. Well, it's time to put all these parts together so we can commence the testing. The test stand has an eyelet up here at the top, and we'll hang one of the hooks of the ram on that eyelet. Now this ram's a little bit heavy, so lifting it by one arm, it works, but I'm getting old enough to where it's a little bit heavy for me. I want to adjust these hooks on the ram so they're fairly straight. I want to try to avoid any twists in the links that go from the top all the way down. Otherwise, when I put a load on it, it'll start trying to put a twisting motion on the rib, and I don't want that. Okay, next thing is to put the load cell on the bottom hook of the ram, and then I'll run the cable from the load cell over to the side of the test stand on a little hook there to keep it out of the way. Now on the bottom of the load cell and the eyelet there, we're going to put a quick link in there. And I have a little hand pump, a hydraulic hand pump to operate the ram. I'm going to hook up the hydraulic hose from that hand pump up into the ram. I want to put the display for the load cell where I can see it on camera and also at the same time see the nose rib. So when I have a failure, if I need to, I can go back and look at the video and see what the load was at the time of the failure. But you'll see that view a little bit later. And then of course I need to attach the display to that same cable that came out of the load cell. Okay, next thing to do is hang that Whipple tree from the quick link. And then I put the rib assembly, which includes the little stand for attaching it to the test stand. I attach that to the bottom of the test stand. I have some all thread that goes down through the test stand and then some nuts to bolt the test stand to that all thread. I forgot to adjust the camera here so you can see that, but you'll get to see it shortly because I have to readjust the height of the nose rib. Well, after I got all these parts on here, I realized that the Whipple tree is a little bit too high. The load wires that go from the Whipple tree down to the load tabs on the rib couldn't reach. So in order to fix that problem, I added some chain links between that top hook on the ram and that eyelet at the top of the test stand. And that's just so I can lower everything down a little bit lower. And then once I get it down low enough so that the load wires on the Whipple tree can reach the load tabs on the rib assembly, then we got it just right. Now, the Whipple tree is a little bit aft heavy, so it wants to tilt the front up and the back end down. So what I'm first going to do is to get it level. And I'm going to do that by attaching the front load wire to the front tab on the rib assembly. And then once I get that, I'm going to attach the most aft wire. And that'll hold the Whipple tree in the correct orientation. So once I get those two, then I go ahead and attach all the rest of the load wires from the Whipple tree. Once I have all those wires attached, I can then go back and loosen all the bolts on the Whipple tree so that all of the load beams can swivel freely. And I need to do that in order to get all the loads distributed correctly. And then I go back and finish twisting up all the wires, since now that I'm happy, none of the load beams and the whoops tree are touching each other. I got good separation. Everything's pretty much vertical. And so I can go ahead and finish twisting the wires that are going through the load tabs and getting them firmly attached so they don't slip out. Now I noticed that after I finished attaching all the load wires, you don't see it here, but the load showing on the load cell was about 15 pounds. And I knew that was too much. By attaching those load wires, I actually added some load. So I decided to alleviate that issue, I'm going to raise up the rib assembly a little bit. So I took off the nuts from the all thread that attached it to the load stand. I put one nut back on the all thread all the way down, so that it actually raised the level of that rib assembly by 1 nut height. And that was enough to take the load off. And then I measured the load, and it was 2.6 pounds. So basically that's a whoops tree, the wires, and that quick link. Weighed about 2.6 pounds. I ended up not really considering that when I'm doing my load test, because it really wasn't that much. But if it had been quite a big load, then I would have taken it into account. I don't have any background audio here for this next section where we're going to do the actual testing. And that's because I invited some patrons to come and watch on our Discord server as I was doing the testing. So we were doing a lot of talking back and forth, and that was a lot of great fun doing that. But I figured during this video, hearing all that in the background would be distracting for you, so I've muted out the sound here during the testing part. But if you might want to become a patron and or join the Discord, you can certainly do that. Here on the screen is the URL to get to the Patreon. And down in the description, there's a link on how to get to the Discord server. You're certainly welcome to join. Well, now it's time to get on to the testing. Now the plan for the testing is to go up to the 3.8 G load first, and that's around 87 pounds. Then I'll come back down to 0 and then check to see if there's any permanent deformations. Is the rib bent any? Are there any dents? Has there been any permanent problems to the rib? And there should not be. Now once we've done that, then I'll crank up the load again, and then I'll go to the ultimate load. So that's a 3.8 times 1.5, and that's up around 131 pounds. And then I'll take the load back off again, and we'll check and see if there's any permanent problems with the rib. Now it's very possible there will be. I wouldn't be too surprised if there is. Although I'm hoping there won't be, because I'm hoping that this rib will perform better than the cantilever style rib that I did before. So while it's up at the 131 pounds, I'm going to check the rib, I'm going to look at it, I'm going to feel it, I'm going to try to see if there's any deformations. Then we'll take it back down to 0, check it again, and it'll be much easier to check for deformations when it's back down to 0. It could be temporarily deformed up at a higher load and then have that deformation disappear when it goes back down to 0, because it's not a permanent deformation. And then after that, we'll take it back up and we'll keep loading it until it fails. Now the way I'm going to apply the load is with a hydraulic hand pump, but I'll stick a little picture up here on here so you can see at least what part of it looked like. I didn't take a great picture of it. And that's off to the right here. You can't quite see it here in this view. It's just to the right of this view. But you can see in this view that there is a load display, so I can see how much load I'm applying to the system. Now after I increase the load a little bit, not too high, but get some load on it, I go and check the tension on the load wires. I want to see if there's any that's loose. If there's something that's loose and others that are tight, that means I've got something wrong with my whipple tree, and I'll have to go back and check that. But it turns out that all of them are getting some load on them, so that's good. Now, as you can see, each pump of the hydraulic handle, you can't see the hydraulic panel pumps, but you can see the load increasing from, roughly 5 pounds to 10 pounds. So each pump is adding quite a bit of load to the system. So I'm doing the pumps not fast, but not slow either. After I got up here to about 26 pounds of load, I also wanted to just kind of wiggle those load tabs a little bit. I wanted to see if any of them had come loose yet. I didn't hear anything, but I wanted to at least physically check a few of them, take a look, make sure that, that the super glued is still holding those load tabs down to the skin. So as I'm increasing the load, I'm paying a lot of attention to what's going on with it. Number one, I'm watching the pressure. If I get a sudden drop in pressure, that probably means something failed in the aluminum. And I want to pay attention to what pressure that happens at, which is one of the nice things about doing a recording here. I can go back and look at the recording and see when something failed if I don't happen to be looking at the display when it happens. I'm also listening. I'm trying to see if there's any popping sounds, any groans, any moans. At least groans, moans not coming from me, from the metal. And I'm also looking for any distortions in the shape here that I can see of the rib or from the airfoil shape of the skin. When I got up to 56 pounds of load, I wanted to stop and do a check, see if I could see any distortions in the rib, but I don't see anything. It looks good, so proceeding on. Now at 84 pounds, I should have gone up a few more pounds, up to like 88, 89. I did a stop again, so this is roughly our 3.8 G load. I want to check really good to see if there's any issues with the rib at this load. It's got to be able to avoid any permanent distortions, any permanent damage, and so it's time to check it out. Now, one thing you may notice here, if you're looking at the load scale here, is that the load is just slowly dropping over time. And there are at least two reasons for this, possible reasons. One is that there's a very slow internal leak in my hydraulic system. There could be a leak in the ram, and or there could be a leak in a valve down on the hand pump, or in the pump itself. The other possibility is these load wires that I have on here. Each one of them has just a little slight kink in it, a little bit of a bend, maybe several bends. So it's possible that at this load, those bends are slowly starting to straighten out and elongate a little bit, and that would reduce the load too. Now this load has lifted or slightly moved the whole assembly here just a little bit. So I'll do a before and after internal shot here of the rib and the skin. And so you can see that it is lifting it just a little bit. Well, the rib looked really good here at the 3.8 Gs. So I decided to go up a little bit closer to the safety factor limit. I went up to 104 pounds and decided to take a look at the rib and see how it looked here at this load. Well, it's time to do a visual inspection, a little tactile, a feeling inspection, and let's see if I can see any distortions in the rib, any problems in the rib. Well, after checking it out, I really don't see a problem. Rib looks good, Whipple tree looks good, load tabs look good, so I'm pretty happy with the test so far. So it's time to start increasing the load again. Now I decided not to release load and go back to 0 to see if there was any undeformation, just because I couldn't see any deformation here. Because basically there'd be no difference going back to 0. So there's no sense in going back to 0 here. So it's time to increase load and keep testing. So I started adding load again, and I only added another, 10 pounds or so. And I started checking, and I could feel some deformation. What I was starting to feel was the web on that top beam that's holding that top skin. That web, as I was feeling along there, I could feel it rippling just a little bit. And I imagined that was because the dimples in the top flange of that beam. I think what was happening at each one of those dimples, there was, because of the stress in that beam, it was probably starting to warp that beam a little bit, and I could feel it as I ran my fingers along it. So it was starting to get me a little bit worried. So I decided to go ahead and remove load and then check it without any load and see if those ripples were still there. I didn't think they would be, and they were not. So everything checked out, no permanent deformations at 0 load, so it was time to load her back up. Now you can watch and see the Whipple tree in the upper left start to rise up as I start to apply pressure. Pressure really isn't increasing, but the ram is starting to lift as I'm doing these pumps. And then as it gets up a little ways and starts getting tighter, then the pressure starts increasing. And now we're taking the pressure up to our 3.8 G plus our safety factor 50% more. So it's going to go up to around 132 pounds. At least that's what our goal is. And once we're up to 132 pounds, we have not failed. So that's fantastic, which is way better than the cantilever rib that we had before. But that cantilever rib failed at 116 pounds, had a permanent deformation. Well, this rib's made it up to 132 pounds. It does not look like it has any permanent deformation. So this is fantastic. This truss style rib is really working well. Working better than I thought it would. But let's release the load on this rib, and let's be sure that there isn't any permanent deformation. We'll stick our hand in there, feel around, particularly on this top beam, and I think I'm right. I don't see any permanent deformation. So this rib has performed fantastically. Now, I am happy with how this rib's behaving at 132 pounds, but I really want to know when it's going to fail. I mean, just how good is it? So let's load this back up again. So start pumping it up, start putting load on this rib. I get it up to 150 pounds load, and it hasn't failed yet, but I'm curious just how much deformation, at least non-permanent deformation, I have on it so far. So we're going to stop and feel around in there and take a look. And the web of the top beam of the rib is definitely getting some ripples in it. You can definitely see some deformation. And let me show you a before and after. I'll alternate back and forth, and you can see when it's nice and smooth and a little bit lower. And then with the 150 pounds, it's been pulled up and we've got some ripples appearing. So it seems like it's probably getting close to failing. So let's put some more load on and see when it fails. Watch this location here and the load as we increase pressure. Well, for a brief instant, it made it up to 159.8 pounds. And it was a really brief instant. And then it failed. And what failed is the bottom flange on that top beam right there where that arrow is. Now, I was able to tell that it failed even without being able to look at the rib. I was looking at the pressure and I was listening, and I heard kind of a little moan. It wasn't even a pop. And then I saw the pressure rapidly dropping. So I knew something had given way. Let's take this back into the shop. We'll take a little closer look at it and kind of do a summary of what we learned. Well, let's summarize what we've learned. Using super glue to put these tabs down, that worked. I thought some of them would pop off, but none of them popped off, so I was very pleased with that. And the maximum load that we should have had was probably on this front tab, and about 20 pounds of load on that. So any more rib testing, I know that at least this much surface area with super glue will work. My test stand, that seemed to work out fairly well. 150 pounds of load wasn't really that much for that stand. I designed it to go up to about at least 2,000 pounds. So that wasn't really much of a test for the stand itself, but using the ram worked fantastic. The load cell worked great. The Whipple tree worked really good. So I was very pleased with that. So I'll keep using Whipple trees, and I can reuse parts of this Whipple tree. The little stands I welded up, these guys, they worked out pretty well, even though it had been a couple decades since I tried to do any stick welding. The welds are horrible, but I knew they could at least handle 150 pounds, and they did, and they worked great. The spar I've been using, just like with the cantilever style rib, that's still working great. The rib spacing, a 2-inch rib spacing, that works good. I did not have a collapse of the skin back here. The maximum load that I wanted to make sure that this could handle, the 130 pounds, it passed that with flying colors. In fact, even going up to 130 pounds and then reducing the stress on it, there were no permanent damages even at 130 pounds, which is at the maximum of the safety factor. So that's fantastic. And when it failed at 155 pounds, it was still carrying 130 pounds after the failure let some of the load off. It was still carrying 130 pounds there, roughly 130. So that's pretty good. So even after a permanent failure at 155 pounds, it was still carrying at least 130 pounds of load. So that's still pretty cool. It failed where I expected it to fail, and that was up here in this upper portion of the rib right up in here. I figured that's where it would fail. This bottom flange on this top bar of the rib, it was going to be in compression under there, and that's where it should have failed, and that's where it did. Now this rib could be, with a very small modification, basically making the web or the depth of this beam a little bit more, a little bit higher, that'd be able to handle even more load. It'd make it slightly heavier, but you might be able to drill some lightning holes along the web. And it could easily, maybe with the same weight, have it carry even more load, but there's no need to. It only needs to carry 130, it might clear up to 150. Now for you guys who have done a lot of testing and know how to do testing, of course, this one sample doesn't really give you the full story, especially since it's being made by hand. If you make something like, what, 20 ribs for an airplane, no two of them are going to be exactly the same. They're going to be slight variations. And so to really do good testing on this, to see on average if it's going to fail at roughly the same point, or at least fail over the 130 pounds, I'd have to probably test 20 ribs and get some statistics, and then use those statistics to try to validate design or see if the design has to be made better or the process of making the ribs needs to be improved. Let me put a picture up on the screen, and I'll put some arrows where it failed. Now, it also failed up here closer to the nose too. I'll put a couple of arrows up there where there's some very slight permanent deformations. That's a little bit of a failure, but it wasn't enough of a failure, I think, to make a difference. I don't think it wasn't a collapse, but it was getting very close to being a significant failure. So I probably will make a slight change there. I'll probably make that curve just a little bit more round, a little bit bigger radius, and that'll take care of that issue. And this test isn't a perfect test. I put all the load on the top skin. Now in flight, that's not the way it's going to be. There's going to be somewhere from 20 to 30% of the load up here near the nose, underneath, pushing up. Now, I did not do that in this case. So some of the load that I put up here on the top would actually be underneath. Now that means this beam up here would have less load of it, even though let's say we had 150 pounds total. The load on top would be 20 to 30% less than that, which means the overall load could probably go even higher before there's a failure, because some of that load would be pushing under here. Now, when you're pushing under here, there would be a little bit of a load on this bottom beam, but not nearly as much on the top beam. And they're basically the same construction, same length. So I don't think that would fail. There would be some compression on this beam here, this little portion, but that is short enough that I don't think there'd be an issue there either. So I think that this test that we did is good enough, but we're not done yet. We still need to test in the negative orientation. So in this case, we need to do the test again, except we're going to pull up on the bottom. And what we did on this one was 3.8 Gs and then multiply by 1.5 to get to the 130 pounds of load. In this orientation, we only have to go to 1.5 Gs, and then again multiplied by the 1.5. Now in that case, this member here will be in compression. And when it fails, I'm guessing that this component it'll get crumpled and fail. It'll be a column failure. So the next time we do a rib test, that's what we're going to do. And we'll reuse the spar again. We'll probably reuse this sheet because the sheet did not get damaged, but we do need to make a new rib. Now when I go to make this new rib, I'm going to use a method similar to what I did for this one. I did hydroforming on this, but I did it over here on my very small hydraulic jack with just rubber in a 12-inch by 12-inch area. And since the rib was bigger than that, I had to keep moving it around and putting a little more pressure. Well, I'm going to make a new hydraulic press to do this, and it's going to have a bed that's 2 feet by 3 feet. And that'll give me enough area that I can also make the main rib for the ultralight. I'm going to have to make the press though, because I can't find one anywhere. They might make it, but it's probably too darn expensive. So I'm going to buy the materials, because I do not have enough materials to build that just laying around. So I have to buy the materials. I'm going to weld up this new press, and I've already got the bottle jacks for it, but I need to make the table part of it. So that's going to be my next project. It's going to take me a few weeks to get it built probably. So it'll be probably sometime in August before I put out the next video. And the next video will be using the table. I don't think I'll make a video making the table, but I will make a video using the table to make the next rib. Well guys, thanks for watching. Till next time.